Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
So I'm going to talk about a subject which is dear to my heart, but is also known to be quite technical. So I hope that you will enjoy your time and also at the end of the talk. So the first question I want to start out talking about is really fundamental to what my talk is about. And that is, what is everything around us made of? What is stuff made of? So for example, if I take a cow, well, we all know what a cow is made of, right? I mean, it's made of steaks. So, so I could end the talk here, I guess. But let's try to be a little more specific. So if I look in a little more detail at these steaks, then they're made of they're made of muscles, and inside the muscles, they're made of some cells. And the cells have DNA inside, and these DNA are made of molecules, and the molecules are made of atoms. And at every step here, I go down to something that gets smaller and smaller and smaller. And you could keep sort of opening up these boxes and ask what's inside, what's it made of? That's one of the key questions that we want to know. What are things made of? And the stuff that it's made of, how does it talk to each other? So let's go with atoms. What's inside an atom? Well, an atom kind of looks like this. There are some electrons going around a central core, which we call the nucleus. Then we gotta ask what's inside the nucleus. Well, we look inside the nucleus, and there are protons and there are neutrons. So there are some other particles, okay? So we look at the protons and the neutrons, and we look what's inside of those. And inside of those are something called quarks. So a proton is made of 2 up quarks and a down quark, and a neutron of an up and 2 downs. Well, actually, that's not exactly true, but it's roughly true, and we'll get to that a little later. So these are the questions. What is everything made of? So let me phrase it a little more technically. What are the elementary building blocks? What are the smallest Legos in nature that everything is made of? Question 2, how do you build these Legos together? How do you attach them? How do they talk to each other? Or more technically, what are the fundamental forces in nature through which these elementary particles interact? And then you can ask, well, given that we could try to understand the first 2 questions, where did all these things come from? How did the universe begin? How did it evolve? And where is it going to go? Where is it going to take us? These are some of the fundamental questions that we ask in particle physics and in cosmology. Cosmology is really more the third type of question here. And I'm going to focus more on the first 2 parts in this talk. So how do we study questions in particle physics? Well, we can do 2 things. We can do experiments, where this is an example of one that's currently running, the Large Hadron Collider at CERN. Here's an overview picture. There are these protons from inside the nucleus. They run in opposite direction around along a large ring, and then they collide with each other at high energies, and we try to understand what happens in those collisions. But to extract information from all these collisions, then we have to know something about the underlying structure of how particles interact with each other, and that's where the theoretical predictions come in. And the subject of today are really these theoretical, how you address these theoretical questions, and I'll refer to the experiments once in a while. Okay, now the framework for all this, as you know, because you read the title of today's talk, is relativistic quantum field theory, and I advertised it as the mathematical language of particle physics. So you should really think of this as a framework for which we can do calculations and then compare to the experiments. What I want to try to get across to you is a little bit of a sense of what quantum field theory is and why we need it. So the first question is indeed, why do we need quantum field theory? And secondly, what is it actually? So given that we know what it is, what do you do with it? And I think it's also fair, so briefly at the end, I'll say, well, I mean, quantum field theory is something that was developed for more than 50 years. So given that I'm giving this talk now, what do we do with it today? Why are we still excited about quantum field theory? And I'll comment briefly about that towards the end of the talk. So this is where I want to go. So why do we need quantum field theory? Why isn't it good enough to just have regular, good old quantum mechanics? Why can't that just cut it for us? Well, let's have a look. So we looked at atoms, the nucleus, we looked at protons. Now, atoms are some rather small things. For example, they are a lot smaller than a cow. So if we look inside the atom, then the nucleus is a lot smaller than the atom. And the proton, even so, is a lot smaller than the nucleus. So we have to study these structures. And suppose I want to study the nucleus. I can take a probe of structures. I can try to probe the structures by shooting something into it. And so one thing that was done very early on in the studies of what is inside everything was Rutherford's experiment in 1911, where he shot alpha particles, which are actually another kind of nuclei. He shot them into a thin foil of gold, and he tried to see and understand some of the structure of atoms. Now, if you look at this and you want to probe something of the structure of an atom, size of an atom, to probe the size of the nucleus, then it requires an alpha particle to go at a certain amount of energy to actually get close enough to the nucleus. It's going to be repelled from it, so you need to get close enough. It needs a certain amount of energy, and to have that amount of energy, it needs to go fast enough. But fast enough is only a tiny fraction of the speed of light. This means that we call it non-relativistic, meaning that it's something that we can describe basically with classical mechanics. Okay. So let's go a little deeper. Let's try to probe what's inside the structure, the scale of a proton, by shooting electrons into it. So here comes an electron. This is really getting into a little bit of quantum billiards. You shoot the electron into the proton, but to probe this sort of small structure, the electron needs to go really fast. And actually, you could kind of calculate, it requires that it goes at very, very close to the speed of, very close to the speed of light, about 99.999% of the speed of light. So that tells us is that we really need Einstein here. And Einstein helped us describe what happens when things go that fast. Namely, you have to use his theory of special relativity to describe it. So, to summarize this, when you need to probe small scales, in the top line here, it requires going to very high energies. High energies you can get by making the particles move very fast as you shoot them into something. And as they go very fast, we need special relativity to describe it. So this is one reason, but I'm going to give you some more. So let's say a few words about special relativity. So I'm pretty sure you recognize E equals mc squared. Well, in fact, when you see this, the first thing you probably think of, well, there could be two options. The first thing you might think of is, where did all the donuts go? Are there somebody eating them out there? Second thing you might think of is Einstein. And that's a little closer to what I had in mind. So Einstein came up with this, E equals mc squared. And what this says is that energy is really the same as mass, and mass is energy. So that means if you have energy, then you can make mass out of it. You can make particles out of it. If you have a lot of energy, you can make very massive particles out of it. So let's do an experiment. We take protons and we collide them with protons. Well, one thing that could happen is that protons come out. You play billiards, you shoot two billiards, you shoot one billiard into the other, and they come out at some different angles with some different speeds. This is something we can do. But now suppose that we collide them with so much energy that a proton and its friend, the antiproton, could be created out of that amount of energy. So if that happened, then all of a sudden I wouldn't be looking at a process like billiards, where 2 billiards are there initially and 2 billiards are there finally. All of a sudden I'm looking at a process where I'm shooting 1 billiard ball into another one and 4 ones come out. I haven't tried that, as far as I remember. So I'm looking at this process. Proton, proton goes to proton plus proton plus proton plus antiproton. And this is very strange, because this is something I cannot describe in regular quantum mechanics, this creation of new particles. And so certainly I need something new. And much more generally, when we collide particles at very high energies, we don't need to consider just the process of 2 coming in and going to 2 or going to 4. We need the processes of 2 going to many. We need to consider all of them, it seems. That is one thing that quantum field theory can do for us. I want to give you one more result. So this is a theoretical physics lecture, so you would blame me if I didn't show you some equations, right? So I'm showing you one equation here. This is the Schrödinger equation from quantum mechanics. So it says something about something difficult with 2 derivatives on something which is called the wave function. And then there's some stuff in the middle. And then on the right-hand side, these are technical terms, don't laugh. On the right-hand side of this equation, you see that there's a single derivative with respect to time. So to summarize the contents of this equation, there are 2 derivatives with respect to space on the left-hand side and 1 with respect to time on the right-hand side. But if you wanted to do special relativity, then time and space are sort of put on an equal footing. And this doesn't have time and space on an equal footing. So it's not going to work with special relativity. And indeed, something else is needed. For example, this equation won't tell you E equals mc squared. It just won't. Now, if you really want to know the details, then instead of the Schrödinger equation, you'll need something called the Klein-Gordon equation or the Dirac equation for electrons. Klein-Gordon equation would be for something possibly like a Higgs boson that you might have heard of. Or you could use Maxwell's equation. That might be a little surprising. Maxwell's equations, that sounds like something from electrodynamics. Why should it know anything about special relativity? But it does, because it treats light. And it actually knows already about special relativity, which is quite interesting. So, good old quantum mechanics won't do. We need something else. And one of the reasons is that we need to incorporate special relativity. We need to incorporate particle production. And that's something else that does it is called relativistic quantum field theory. Now, as a side comment, let me just say that quantum field theory is a wide range of stuff. That's another technical term for you, stuff. So it's a wide range, and it describes a wide range of phenomena. What I'm concerned about here are applications in particle physics. That's why I'm emphasizing relativistic and special relativity. But there are applications of quantum field theory and condensed matter physics which don't care about relativistic speeds. And so just to give you a little bit of context, then I'm talking about one special form here, which is the relativistic quantum field theory. Okay, so we need quantum field theory, but what is it? Even if I break down quantum field theory, then I could ask to begin with, what is a field? So let's try to talk about what is a field. So let's look at something that we look at often, which is a weather map. Here it's given a weather map that shows us the temperature at different places around the country. So at each location you see this weather map tells us what the temperature is. So at every position there's going to be a temperature. It's a little bit like in this room. If we took everybody's temperature, the numbers will come out in slightly different numbers, but I would have to every one of you assigned some number. This is roughly what a field does. It takes a position and it assigns a number. It does a little more than that, but let's see. Another thing you do with weather maps is, for example, to figure out what the speed is of the wind. So you want to know something about the wind. So if I tell you that today the wind blows with 5 miles per hour, you would say that's good, but where does it come from? I mean, which direction is it blowing? So you want to know something more, not just a number. So you need both a number for the strength of the wind, but you also need a direction for where it's going. So at every point, instead of just having a number, you have a little arrow, and the length of the arrow indicates how hard it's blowing. So we're right there in Michigan, and we have some wind, and it's a bad sign that it comes sort of a little bit from the north, because it means it's probably going to be cold. Now, this is also a field. So at every position, it describes a direction and a number, and a length. Another kind of fields that you may have run into are electromagnetic fields. So if you have a magnet and you have a compass needle, then I can put this compass needle at different places around the magnet, and the compass needle will turn, and that will show you a direction. And you also know that magnets have strengths. For example, they're the ones that you put on the refrigerator that are really good, and they keep all the papers and notes up. And then there are the ones that always fall down when you close the refrigerator. I don't know why I have more of the latter. So there are these, so magnets also have strength, but there are also directions for the fields. And so this is one of the examples of what we would call a vector field. And you see this comes up, there's the electromagnetic field, the magnetic field of the Earth. There are also electric fields from charges, and so on. So a little more technically, a field is again something that takes a point in space-time and spits out a number. Spits out some number, but possibly more numbers. If it just spits out one number, a bit like the temperature, then we call it a scalar field. And if it spits out something that also has a direction, then we call it a vector field. At least it's part of a vector field, something like the electric field. Now this is a little loose. Actually, they also need to transform in some certain ways, these fields, under Lorentz transformations, but I'm not going to go further into that. But this is what you can have in mind as a field. Okay. So to talk about what we do with fields, let's go take a step back and talk about what do we do in classical mechanics. So in classical mechanics, we solve Newton's equation, and the result of that is that it gives us the position of our billiard balls as a function of time. We know where they go, we know their initial conditions and speeds, and we know exactly where they're going to go. For example, the Earth going around the sun would be such a case. Oops. In quantum mechanics instead, then we have Schrödinger's equation replacing Newton's equation. And what we describe, instead of a position for every time, we have something called a wave function. And the role of that wave function is that it gives us probabilities. So when you go from classical to quantum, everything becomes probabilistic. You don't talk about that the particle goes here at a certain time. You talk about what is the probability of measuring a particle at a certain space, at a certain place, at a certain time. So everything becomes a probability instead. All the questions you ask are about probabilities. So this is a big change from classical to quantum. Now let's go to quantum field theory. Now we have these fields instead. They depend on space and time, but they're not wave functions. You don't take the square of them and interpret this as probabilities. Instead, actually, well, I'll tell you instead what you do with them. But actually, I should just mention that working with these fields is actually a little bit like working with quantum mechanics, but where you sort of have infinitely many degrees of freedom to work with at the same time. So what do you do with a quantum field? Well, a quantum field, well, it's not something that gives you a probability. It's something that can create and destroy particles. And this is exactly what we wanted, because we wanted this idea that when we shoot things together with sufficiently high energy, then we can create new particles. We can create more particles. And so this is exactly the right thing that it should do. It creates and annihilates particles. So in some sense, technically, particles, what we even talk about as particles, are little fluctuations of these fields. And when we talk about particles interacting with each other, we understand that as how these fields talk to each other. So let me try to give you an example of this. So I'll declare that I have some field that is this Greek letter psi. It creates an electron. And I take one that destroys an electron, and I just give it the name psi bar. And then I take a field A to be something that creates a photon. So if I wanted to create an electron and a photon, then I would use a psi and an A. And so if I want them to then interact together, then I can draw this diagram. I want them to interact together, and out comes another electron. Well, out comes the electron, but maybe changed its momentum a little bit. and that will then be destroyed at the end of the process, so I put a psi bar. So I have the creation of the electron here at the end of the equation, the psi. I have some matrix, which is called the gamma matrix there. Then I have this a mu that creates the photon, and then I have the psi bar that destroys the electron. And then this is all multiplied by the electron charge, just for good measure. And then I draw a diagram that encodes exactly that, and I translate that diagram to whatever wasn't the things that destroyed the particle or created them. So this is very, very abstract, right? I mean, I draw a picture, and I draw some math, and I put it together, and I say this is how it works. And I didn't make it up, actually. I mean, this is true. This is the way it works. So this is how we do it. For every particle that we want to describe, we have a field. And for every time we want these particles to talk to each other, we write some term that multiplies these fields together. And actually, secretly, what I've introduced to you now are Feynman diagrams. So here is 2 copies of what we just talked about, stuck together into one diagram. And what it describes is, if you read from the left to the right, is that 2 electrons come in. They feel each other. They say, ooh, bah, this is the same charge as me, and then they run away from each other. And the way they say, ooh, bah, technically, is that they exchange a photon between them. So, in other words, what you normally call electromagnetism, where you have 2 electrons being repelled from each other through electromagnetic forces, is what in quantum field theory described with such a diagram here. Electron, electron coming in, electron, electron coming out. And so the other thing I mentioned was that each of these little pieces of the diagram have a mathematical description. So every time I write down such a diagram, it's really a way for me to remember what kind of mathematical description this was. So Feynman diagrams are mathematical expressions. So what do you do with these things? Well, these things combine, and you use them to calculate probability amplitudes. So taking a step back, in quantum mechanics, I got probabilities for various things to happen with particles. I do the same, actually. It's quite amazing that some of the same principles for quantum mechanics work in quantum field theory too. And I can get probabilities out. It's just a different process of doing it. So I can use these Feynman rules to calculate probabilities for processes to happen. And these are closely related to things that are called probability amplitudes. So you look at the bottom of the page here, you'll see an example of 2 diagrams that are involved if I really want to calculate fully what happens in the electron-electron repulsion process. And they look exactly like this. The only difference is between them in the second diagram, the 2 lines are crossed instead of at the first one where they just come straight out. And Feynman's rules are that if you want to study a process, you have to write down all the possible diagrams for it, translate each of them into mathematical descriptions, the mathematical expressions, and then sum them all up. That gives you the amplitude. Then you work a little bit with that amplitude, and it gives you something called the cross-section, which is something you can go out and measure. Or at least our experimentalist friends can. So, how do they do that? Well, every collaboration needs a leader. And so you see, I guess you can identify who's the leader here. The leader on each side, they collide stuff together and stuff comes out. So here at the end of the picture, you have the boss standing, and the boss always needs some people to hold him up. And then there needs to be stuff that you throw together, and the interesting part is to figure out what is going to come out of that. And so exactly how things come out, what comes out, how it depends on the energies, how it depends on the angles at which they come out. This is exactly what we calculate with Feynman diagrams. So, okay, so that's quantum field theory. What can we do with it? Well, you could get a Nobel Prize with it. And so did Martinus Weltman, who was a professor here in Michigan. And he shared it with Tufte in 1999. Go blue. The other thing you can do is that you can describe all the particles that we've seen so far in nature in quantum field theory. And the quantum field theory that describes it is called the standard model of particle physics. So here's a picture outlining some of the particles that we know. So on the top left in the red piece, you have quarks, which are the up and the down that we talked about, that protons and neutrons were made of. And then they actually have two cousins, two other families that look a lot like them, but they're just heavier. And they're called C and S, charm and strange, and T and B, top and bottom. Then we also have our friends, the electron, and its cousin is much lighter and doesn't quite look like it. It has a neutrino that comes along with it, but it also comes in three different families. There's the muon and its neutrino, there's the tau and its neutrino, all there in the green block. And these particles are what stuff is made of, even cows. And these particles talk to each other then through forces. And the forces are given here in purple. You have the photon, which is this gamma listed. You have a G, which are gluons. Those are the ones that help quarks talk to each other. And those are the ones that encode the strong nuclear force. Then you have the C and the W of the weak nuclear force. And now you see there, sort of hiding in the back, in gray, is an H for Higgs. And that's the much sought after Higgs particle that you probably heard a lot about in last week's Saturday morning lecture, perhaps with Gordy Kane. And it's just really at the verge that this should be found at the LHC. And there's already been results reported, and I'm really waiting for hear more updates about this. We'll have a workshop on this later in this semester here in Michigan. And it'll be very exciting to hear what the latest results are when we get there. But all of this is described in the quantum field theory called the Standard Model of Particle Physics, which means that you can take all these particles that I show you here. There's some field that describe them. There are some terms that tell how they interact with each other. There are Feynman rules for calculating how they interact with each other. And using those Feynman rules, you can calculate probability amplitudes for what happens at the Large Hadron Collider at CERN. And you can calculate it to high precision, and you can compare it with experiments. And so far, everything that we have seen, but so far what we have seen is that things agree extremely well between the standard model and experiments. Of course, we're really interested if there's something else that we haven't figured out yet that might be there beyond the standard model. And so we look for tiny differences between what the experiments see and what the theory predicts. And we try to come up with new theories that describe physics beyond the standard model to test it at experiments like the LHC. So this is a very exciting time for particle physics, and it's a very exciting time for quantum field theory. Here's a picture from the ATLAS detector at the LHC. This is the first picture on the left is from the assembly of the detector. And what to keep in mind there is if you look very carefully, then there are two people standing down in the little orange area to the left. It gives you a little bit of a sense of the scale of how big this machine is. And you can imagine if it's your job to wire it all together, that you'd be pretty busy and you have to work very hard to get it all fitting together. Here's a picture from the ATLAS detector, a reconstructed event. And you can see then that you need a lot. I mean, here protons are shot together with protons, right? 2 in, 2 out, roughly speaking. But you see all these tracks are from particles produced in the event. So it's certainly true what I told you, that in these collisions at very high energy, sprays of particles can be created, and you need to understand how to calculate it. This is just what roughly illustrated in this figure on the left here, protons coming in, sprays of particles coming out. You need very careful analysis and statistics to understand all these events. So let's come back to quantum field theory a little bit. So Feynman tells us that the way to calculate an amplitude for these particles coming in, going out, can be described in terms of his diagrams, the Feynman diagrams, which, by the way, appeared on his van that you see here on the picture. So he could show people what they look like. Each of these diagrams are mathematical expressions that we need to figure out how to calculate, but there's also a very nice organization of these calculations, which is that you write the diagrams and you count how many closed loops you have in each of the diagrams. And the fewer loops, typically the more it contributes. So this is the lowest, the leading order contribution is called tree level. And then one loop gives the correction to the tree level, 2 loops gives the next to leading order correction, and so on in the expansion. And depending on how well you can measure stuff, you may only need to go to a certain level in that expansion to understand it. So I thought it would be unfair if I didn't show you what a calculation in quantum field theory looks like. So I took one from my class this past semester, which was the first semester of a quantum field theory class. And this is from the last homework of the year. There'll be a test on this afterwards. So pay attention. So what it shows is what happens if you take an electron and its antiparticle, which is called a positron. They can come together, as illustrated in the first top panel here, the left figure. You can see they can come together and annihilate into a photon, which then pair produces a positron and electron again. And there's another way that they can interact with each other. They can also basically scatter off each other with exchange of a photon. That's the second diagram in that panel. So you write down the diagram. Those are the 2 ones that can contribute to the process. And then you tell the students in the class to calculate the mathematical expressions of these diagrams. And they do it because they're very good students. And then they work a little bit, and they get what is here on the top left panel there. It says IT equals and a whole bunch of stuff. So the first line of that is the first diagram, the second line is the second diagram. And what these things encode are pieces from the diagram. You recognize some of these gamma guys that come in that you saw in an earlier slide. Okay, what do you do with it then? Then you tell them to find the spin sum average. Okay? And they do that because they learn how to do that in class, and they're good students. And you see that then you get what is on the left panel here at the bottom. And it involves some S and T and U and M. M is the mass of the electron and positron. S, T, and U are variables that encode the momentum of the electrons and the positrons and their relative angles with each other. Here's a simpler version. Then you can take the limit where the energies are very high. We can ignore the mass of the electron, and you get something at the end, which is called the differential cross-section. This differential cross-section at the bottom right, is something that you can go to Sackley, you can go out and measure. And you can compare what it says there with experiments. And all this came from those diagrams up there. So this was from the last homework. And I think there's at least one student here who can testify that this was a rather long calculation. It wasn't on the exam, though, so. OK, so now you know quantum field theory and Feynman rules. So it's time for our first midterm exam for today. So did you bring your calculators? All right, so the question is, what are Feynman diagrams? Option 1, they're pretty. I mean, they're pretty. Option 2, man, they're complicated. Option 3, well, they represent mathematical expressions. Option number 4, they're a way to calculate particle interactions. Option 5, all of the above. 6, none of the above. Option 7, there was a cow on one of the first slides. So let's see, votes for number 1. All right, I see 3 votes. 3 votes, that's good. Option number 2, votes. 1, 2, no, 1, 1.5. Oh, wait, number 2, I want to vote 2. And I want to vote to number 1, too. Okay, option number 3, they represent mathematical expressions. All right, I just vote every time, as you see. Number 4, a way to calculate particle interactions. All right, all of the above? All right, that's a lot of votes. None of the above. No votes. And there was a cow on one of the first slides. There are quite a few votes for that. But guys, I mean, it's true, there was a cow on one of the first slides. But the question was, what was a Feynman diagram? There's going to be a second harder exam just because of this now. So the right answer is all of the above. And a lot of you got that right, so that's a good sign. I'm glad you paid attention. Now, I think I have a little bit of explanation to do, because when I say, I say how great they are, they work well to calculate something with experiments, and then I say that they're too complicated. So am I just selling you some big fat story? Well, they are actually too complicated. And I want to show you another example of why they're too complicated. And this example shows it serves two purposes. One of it is that it illustrates really well how great quantum field theory is. And the second one is that it gives you a great hint of why Feynman diagrams are too complicated. So the story starts with something called the electron spin magnetic moment. And so it's this in white box mathematical expression. The thing on the left is called the spin magnetic moment, and it's given by some factor gs times mu b, which is called a Bohr magneton, and then there's an s, which is the spin, and then there's an h bar, which tells you that some quantum is probably involved in all this. So we tell our students that gs is 2. That's what comes out of quantum mechanics. And then you can go out and measure it, and you find that it's close to 2. At least up to a couple of decimal places, it's 2. So you could say, well, good enough, okay. Maybe my experiment wasn't quite right, but then you look at the uncertainties in this, and the experimentalists tell you that they are sure about all these digits up to a very high number. And the reason is that that something really is to this number is that there are quantum corrections that come in and correct this too. And these quantum corrections that come in is something you can calculate with quantum field theory. So remember that I expressed Feynman's rules were that you start with all the diagrams that didn't have any closed loops. Those are the leading order contributions. Then you took the next set of diagrams, there was one closed loop. These are called the one loop corrections. And then the ones with 2 loops and so on. If you take the diagram with one loop, and this was done in the 1940s, then you can calculate the one loop quantum field theory correction to the number 2 for GS. And you can notice that 2 plus this little correction is 2.002323 ... And if you compare that with GS, well, that's pretty close, because now it's 2.002319. So you get the next 2 digits, actually you get them right. So you have 2.0023 compared right with the experiment. But it's not quite right still. And so you need these higher loop corrections to come in. And in fact, people have worked very, very hard to calculate these higher loop corrections. And it turns out, I mean, you can calculate up to and including 4 loops, and you get a remarkable, fascinating agreement with what you see experimentally. It must be one of the most precise measured quantities that we have that agrees so well between experiment and theory. I didn't even really have to write the theoretical part because it looks the same. I think it's about agreeing up to about 13 digits. It's really, really remarkable. So this shows you something that quantum field theory is really, really good at, these really high precision calculations that you can go out and compare with experiments and find great agreement. So I want to focus a little bit about one part of the contribution, which is the 3-loop calculation. It was done in '74 using Feynman diagrams by Cvetanovich and Kinoshita. And the result for it is, well, it's something like 0.92 plus minus a bit times alpha divided by pi to the 3rd power. And so going back here, alpha is the fine structure constant. It's 1/137 approximately. And pi is pi. Okay? So roughly speaking, 1 loop is alpha over pi. 2 loops is going to be alpha squared over pi squared. 3 loops is alpha cubed divided by pi cubed. But then there's some number multiplying it, and that number multiplying it has come out of this very detailed Feynman diagram calculation. To do this calculation, they needed to calculate a huge number of Feynman diagrams. very, very large numbers. They needed computers, and they even had, that was back in the time with punch cards. So you can imagine what kind of effort went into calculating this. And actually, Cvitanovich got a prize later on, and he recalled in his thank you speech a little bit about this calculation. So he'd done the calculation with Kinoshita, and one day, terror struck. I was invited to Caltech to give a talk. I could go to any other place and say that Kinoshita and I had calculated thousands of diagrams, and that the answer was, well, the answer is plus 0.92 plus a bit times alpha divided by pi to the third power. But in front of Feynman. Feynman is going to ask, why did you get plus something, not minus? How can it be that 100 diagrams give the result of order 1, and not 100 or 10 or any other number? This may be the most precise agreement between fundamental theory and experiment, but what does it all mean? And if you think about it, this is really remarkable. You have to calculate thousands of diagrams. Each of the diagrams is about 1 or maybe minus 1. And then you add them all up, and instead of getting something like 1,000 times 1, or 500 or something like that, you end up with a number which is roughly of order 1. I mean, why? Who knows? And so that's really what this question is about. Is there something underlying this that wasn't showing up in the Feynman diagram calculation? And it's sort of for sure that there was. Now, there's a little more to the story. You can group these thousands of diagrams into little pieces, each of which makes more physically sense than the individual Feynman diagrams, because individual Feynman diagrams actually don't make physically sense. So you can group them into pieces, and group them into pieces, you find that each of these pieces are again of order 1 or a half or so, and that actually explains the answer a little bit more. But still doesn't give a fundamental explanation. So this example, well, it illustrated the agreement between quantum field theory and experiment, but it also illustrated that Feynman diagrams, well, are too complicated in some sense. There are many examples of this, namely that you calculate with Feynman diagrams, and it looks very, very complicated, as students in quantum field theory attest. But then once you simplify and you work and you work and you work, it ends up being quite simple. And I want to show you another example of this, which comes from gluon scattering. So let's first take a step back and say, well, gluons were these particles with the force carriers of the strong nuclear force. And the strong nuclear force is described by a quantum field theory, which is called quantum chromodynamics, QCD. Okay, why is this particularly relevant these days? Well, let me go back to this picture of the proton, where we said it was made of 2 up quarks and a down. Well, it's really a misleading picture, because really what's going on inside the proton is there's a whole soup of stuff going on. There are quarks and antiquarks, Q and Q bar, being created and annihilated all the time, and there are gluons roaming around all the time, and what is just there is sort of a net effect of having 2 U's and 1 D. So there are all these particles roaming around inside the proton all the time. And so when we go to the Large Hadron Collider, for example, and we collide protons with each other, it's not just protons and protons colliding and something else coming out. Really, the fundamental particles that end up interacting with each other are all these things roaming around inside the protons. So you can, for example, have a gluon in one proton interacting with a gluon in the other proton. And the sound effects are not exactly authentic, I should say. So gluon scattering is important because it happens all the time at the LHC. And so you need to understand what happens in these processes. So let's look at the process where I scattered 2 gluons to K gluons. If it's just 1, it's really simple because there's just 1 Feynman diagram that describes the process. If it's 2 gluons going to 2 gluons, it's kind of okay. It's 3 diagrams. You can calculate it in your quantum field theory class and get the right answer after a little bit of work. If it's 2 going to 3, to tell you the truth, I've never done it with Feynman diagrams. It's really hard. It's just really complicated. It's not complicated to write down each of the diagrams, but to simplify it down to something that you can put on your sweatshirt, then it requires more work than anybody is really willing to do, I think. And then look at this, 2 gluons going to 5 gluons, nearly 150 diagrams. Do you want to do that? The amazing thing is that if you actually were to do these calculations, you'd find that the answer is really, really simple. The answer for these processes is basically just a single term. Now, I can easily say that without describing to you what this term actually is. It's just this simple mathematical expression, and each of these sort of angle things tells you something about the dot product. It tells you something about the product of two of the momentum vectors, which knows about their lengths, how their strengths are, and their directions. So that's really just what this expression is. And it's pretty wild to think of it that you add up, in principle, so many diagrams, and the answer is going to be so simple. The intermediate stage is an enormous mess, but the final answer is simple. So it gives you two obvious questions. Why is this answer so simple? It has no right to be if you just look at the Feynman diagrams. And given that it is so simple, there gotta be some better way to calculate it than using these quite complicated Feynman diagrams. And there is. I should say, by the way, if you're more interested in this type of formalism, there are textbooks now out on the market that describe it. So this surprising, to summarize what I've said so far, this surprising structure that appears in these probability amplitudes for scattering particles and this surprising simplicity, together with the fact that it turns out that they have really, really interesting mathematical properties, and together with the fact that these are really useful in particle physics, is part of what motivates the current studies of scattering amplitudes. And in fact, we had a conference here on this in this last fall, Amplitudes 2011, with lots of talks and a lot of visitors elsewhere, and a lot of excitement about amplitudes. So this is really an area that's been growing in the past few years, studying how we can do quantum processes for particles instead of using Feynman diagrams, using new methods, and not just finding methods, but also what these methods actually teach us about the underlying nature of quantum field theory. It may help us address what is quantum field theory. So put a little bit of a disclaimer, quantum field theory is a lot more than just calculating particles going together like I described, but this is certainly one place where we can get a handle on things and describe things well. So I just want to show you one slide about what is these latest and greatest ideas. So here are 4 different items on what are some of the latest and greatest ideas in quantum field theory these days. So one of them is that we develop new methods for calculate the amplitudes. These new methods are already implemented in computer codes that are used to compare with experiments. And in itself, these methods are also quite exciting. In themselves, these methods have allowed us to discover new symmetries for amplitudes that if you look at the standard formulation with Feynman diagrams, you would just never, ever have guessed. And symmetries is what theoretical physicists love, because as soon as you have symmetry, it makes your life easier. And we all will like that, actually. So symmetries have been discovered for these. It also turns out, and this is really quite fascinating, that amplitudes are related to geometry. So amplitudes turn out to be related to branch in mathematics, to combinatorics, and other areas in mathematics that describe certain figures in various geometric spaces. And it turns out that sometimes you can understand amplitudes as volumes of some geometric figures. Who would have expected that? And this is still really things that are people are currently trying to understand better. Then I'll just mention one more thing, which is that the new amplitude techniques have also helped us address questions in quantum gravity, to understand this long-standing question of how do you combine all what we know about quantum field theory and quantum mechanics with another great theory, with Einstein's theory of general relativity. How do you quantize it? And this is something that this can help us address. There's, of course, also another framework for understanding this, which is string theory, and that's a different talk, which you'll have to save for another time. So I hope that there'll be many exciting news in the future from this field. And so to summarize, quantum field theory, I hope I've convinced you that it's a mathematical framework for calculating amplitudes, and it's an amazingly useful framework. It's highly relevant in physics, compares with experiments. And one more thing is that it's really also a lot of fun. So there are a lot of people I'd like to thank, and going really far back, there are many people who have supported me in all the years. And it's been a lot of fun to be able to learn some of all these things with all your help. There are also people who have helped in other ways, the Department of Physics, the NSF, and so on. And before I let you go, there's one more thing I'd like to say, and that's a little advertisement for the University of Michigan Society of Physics Students. Some of them are sitting right over here. Raise your hands. So the Society of Physics Students is a physics club, and they do a lot of different things. They organize a talk series with scientific talks aimed at undergraduates. They do it every week, every second week during the semester. They go out and they do demo shows like this one here at the Hands-On Museum at Arbor. Look at the faces of these little kids, fascinated with science. There's nothing better than that. And one thing, the reason I bring it up is that they're going to have a fundraising. And so if you see some of these great young people show up here at Saturday Morning Physics trying to sell you a mug, then please know that they do something really good, and be nice to them. So with that, I'd like to thank you all for coming out this morning, also in the other room. Thanks, guys.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.